All right. Hi, everyone. Thank you for coming and for the opportunity to present. My name is Christopher Agia. I'm a third-year PhD candidate at the Department of Computer Science. I work jointly with the Department of Computer Science and the Department of Aeroastro with Professors Jeanette Bogue and Marco Pavone. And today I'll be talking about some of our research on learning to solve what we call long horizon manipulation problems in robotics with skills and language. So before diving into details, I just want to provide a brief overview of where I believe our research fits in the context of all the great work that's going on today. So the goal that keeps quite a bit of the research community busy these days is in building robotic systems that are multi-purpose, so they're general purpose robotic systems in the sense that they can solve a wide variety of tasks. And we also hope that these systems are accessible to the everyday user. They don't require an expert to work alongside these robotic systems. And so this is commonly characterized as a robot that's operating in a common real-world environment that's a little bit unstructured, such as our house. But where robots have found actually the most success today is, for example, in advanced manufacturing facilities where experts are working with these robots to automate away repetitive tasks in very well-characterized environments. And then there are all sorts of research clusters that one can attempt to fit in this diagram. So for example, in the upper left corner, we have research that focuses, for example, on human-robot interaction, making the interactions between robots and people a little bit more seamless and natural, but typically only does so in the context of one or a handful of tasks. And in blue, we have works such as multitask reinforcement learning, imitation learning methods that try to push the needle on how many tasks we can expect these systems to perform using learning. And there's ongoing research within these clusters that is sort of moving towards the goal. And finally, there's this last cluster, which I'm referring to as task and motion planning, TAMP, which by virtue of the design of these systems, they're able to solve many, many tasks, but they're heavily engineered and require an expert to work with. And so what our research is kind of trying to do is to start with something that's like a TAMP-like system and basically push the needle towards the goal, making it a little bit more accessible, a little bit more scalable towards these future systems. And we're interested in doing this in the context of long horizon manipulation problems, which are problems that exist in our everyday life. We may just not know it. So for example, putting back clean kitchenware on shelves, packing a luggage, and in a very complicated case, loading a dishwasher. And what these tasks share in common is the need to think ahead. So if you place the first mug at the very front of the shelf, you may not be able to place future mugs without collisions. If you don't correctly pack your bag, you're not going to be able to close it at the end. And so we'd want a robotic system to be able to do this long-term thinking. And to ground it a little bit more in our goal, where we want this to be easy for the everyday user, we'd want to be able to solve these tasks from instructions. So here we have an instruction. The human says, could you please move all items into the cabinet? What we'd like our robot to do is to plan a sequence of steps. First, pick up the mug. And then, when the robot picks up the mug, it may realize that it's picked it up in a way that doesn't allow it to be put into the cabinet without a collision with the arm. And so before executing these actions, we want our system to basically rethink and say, no, we need to first place the mug back on the counter, re-grasp it in a way that allows us to successfully put it into the cabinet. And so the challenges here is that these long horizon problems contain many steps, and if every step has some probability of failure, then the probability of failure across the entire chain of steps is quite high. And there's also these geometric dependencies, so as I mentioned, avoiding collisions that you need to consider when solving these tasks. And this is just for one task, right? We want a good solution that's able to resolve these dependencies for many tasks. So I'll quickly talk about three different paradigms for doing this in the literature. One is to use reinforcement learning. Here's just a handful of works. I'm not going to get too much into it. But at a high level, what these methods are doing is they have two phases. In phase A, you want to train an agent here in order to perform these long horizon tasks, these sequential manipulation tasks, in an environment that you've designed and programmed with a reward that you've programmed. So if the agent does something you want, you give it a positive reward and it learns. If it does something that you don't want, you give it a negative reward. And so you're the one, the roboticist is the one that designs this environment and the reward function. And after you've trained the agent, then you're going to want to deploy it into a real world environment. And the deployment phase is quite simple. You just take the learned agent and you deploy it in a perception action loop where it's taking actions in the environment, it perceives the effects of those actions, and it's just acting in a loop. So the advantages is if the environment that you're deploying it in the real world is similar to the one that you've trained it on, you're going to have really strong performance. And the other advantage is that it's very efficient at deployment time because basically this agent is oftentimes just a small neural net that you've learned and you just need to run it in closed loop. The drawbacks of this method is that it is not really showing the generalization to completely new tasks that it hasn't seen at training time. And also, designing this environment can actually be quite challenging for realistic long tasks. And another line of work, so the second paradigm, is in using language models, so things like ChatGPT and large language models, to solve these problems. And there are a few works that have come out over the past 2, maybe 3 years. Seikan, Inner Monologue, Codist Policies are some seminal works in this area, which, in a nutshell, try to combine predictions from the language model with predictions from the robot's capabilities in order to figure out what's the best action to take at the current time step. And what these look like at a system level is you have the language model that sits at the top and starts with the user instruction and is interfacing with a library of skills. These are the capabilities, the low-level capabilities of the robot. So for example, one skill could be how to pick things up. Another skill could be how to push items from one area to another. And the advantage of this method is it supports language natively, which is something that we wanted in our original goals. And also, as you can see, a hierarchy starting to emerge here where we have the language model at the top being able to leverage these reusable skills, these reusable low-level behaviors that it can compose to solve new tasks. The limitations of this method is that it's typically executed in what we call open loop. So this system basically, once it figures out what's the best next step to take, it takes it immediately. It doesn't construct a full plan beforehand and verify that the plan is going to succeed. So you really don't have any guarantees on whether this method's going to succeed. And as you can see in the video above, the complexity of the scenarios are typically quite limited, so low geometric complexity. Our house doesn't typically just have one sponge lying around on an open table. It's a bit unrealistic. But the third paradigm is task and motion planning. And so these are the systems that there's over 2 decades worth of research on these systems. They're quite general. They can solve a lot of tasks. They're quite heavily engineered. So here are 2 pretty seminal works in this area. And as you can see here, we have a 3-stage hierarchy, whereas in the previous one we had a 2-stage hierarchy. At the top, we have a task planner. We have a motion planner at the middle, and the controllers or the low-level behaviors at the lowest end. And what the task planner's job is to basically take a problem and to try to discretize it into a sequence of high-level actions. So for example, pick the mug and place the mug. And it's the motion planner's job to assess the feasibility of this plan and basically communicate back to the task planner if the plan is unfeasible. If it's infeasible, then the task planner will propose a new plan. The motion planner will try to assess the feasibility of that plan. And if it is feasible, it'll be passed down to the controllers to be executed into the environment. So the advantages, this system can generalize to many complex tasks. And you have some guarantees with some of these systems. So for example, probabilistic completeness, which means if you run these systems for a very long time and a solution exists, you're guaranteed to find a solution. But they're very expensive. All right, so every time you give this system a new task, it needs to plan from scratch, which can take minutes. And if the environment changes, you need to replan. And so they're really not yet practical for real-world deployment. They're also quite heavily engineered, so it's difficult to scale them to new domains that they're not engineered to perform on. And what we're trying to do at a very conceptual level is to look at these different paradigms and basically come up with a system that integrates their strengths. And conceptually, this might seem simple, but there's actually a lot of friction points between these pieces, and that's the main challenge. And this challenge presents a really interesting opportunity to do some new research. And so specifically, we're interested in the integration of skills and language, and that's what I'll show next. So we start with a system that looks like a task and motion planning framework. We like it because it's general, it's able to solve many tasks, but it's expensive, it's costly, as we said. And if we go back to reinforcement learning, we liked it because it was efficient at deployment time. And so what we ask is, what can we learn in this framework to make it less computationally expensive? Well, the bulk of the computation time is spent in this middle layer, trying to come up with the actual robot plans and to assess the feasibility of these discrete sequence of steps that the task planner has given us. And so that's what we consider learning. First, we add learned skills to our system, and then we come up with a new type of motion planner that is compatible with learned skills. These learned skills are the low-level behaviors, and we've used reinforcement learning to learn them. And these two in combination give us computational efficiency, as well as the ability to scale up our system, because if we want our system to perform a new task, all we need to do is retrain some new skills and add it to the library of low-level behaviors that the system can use. And so this was the first paper that we published at ICRA. It's called Sequencing Task Agnostic Policies. And at a high level, what we assume in this paper is a library of skills. And I'll go through this. We also assume a sequence of skills that should solve the task if you execute it correctly. But look what happens. In this task, we ask the robot to basically use the hook to pull an object that's beyond its reach into its reach, such that it can acquire that object. But if we just execute the skills one after another, even if the robot picks up the hook successfully, it may not pick it up in a way that allows it to gain enough reach to pull this object closer into its environment. And so it fails the task, even though the sequence of steps is correct. And so the challenge is that there are these long horizon geometric dependencies that exist in the problem. And in order to solve it, what you'd really want is the robot to think ahead, realize that it wants reach, and so to pick up the hook near the edge of its handle. So we want to be able to do this automatically for different kinds of tasks. And so the core idea behind STAP is we're going to formulate motion planning with learned skills as an optimization problem. And we're going to be trying to maximize these actions, A1 through H. These actions correspond to where we're picking up objects, where are we placing objects, how much are we pulling objects by, so on and so forth, to maximize the probability that all skills in the sequence get a reward of 1, which means all skills are successful. And we show under some assumptions that this is equal to a product of learned value functions. The value functions characterize the probability of skill success. And the method is we essentially perform optimization with these skills such that the probability of success for all skills are high. Okay, so how do we train these skills in the first place? Well, we have a pipeline to train these skills, and we want to train them agnostic to the task that they'll be evaluated on. So first we define our environments. These are the environments we'll use to run reinforcement learning in to learn the skills. We then apply off-the-shelf reinforcement learning methods, which provide us with a policy, which is the skill, a Q function, which characterizes the probability of success for the skill, and some data, which is the state, action, next state transitions that are collected over the course of training the policy in this environment. Then for each skill, we train a dynamics model. The dynamics model is used to predict how the state of the scene changes with respect to actions taken by our skill. So this is what will allow us to basically predict how the scene changes with respect to actions into the future. And finally, we train something for uncertainty quantification, but for brevity, we'll leave that out. We come up with a few evaluation domains designed to test these geometric dependencies. They become gradually more difficult, but let's just go into looking at some videos. So this is the first domain, hook reach. This is the example we saw before. As you can see, our method on the left that performs planning is able to capture these long horizon dependencies, pick up the hook near the edge of the handle in order to bring the object closer and succeed at this task. whereas the method that does not perform planning fails. In a different example, we want to place all objects onto this constrained region of the shelf, which is similar to putting items back in a shelf, for example, cups and mugs. And our system is able to plan the placement locations to avoid collisions, whereas the baseline is not able to. And finally, this is the most complicated task we consider, where we want the system to rearrange the position of objects on the table in order to push them under the rack afterwards. As you can see, our system is also able to capture that dependency. And so it's able to do this using the same set of skills. And so in summary, we present this work, sequencing task-agnostic policies. The result is we have a planning framework that can very efficiently solve these long horizon problems. Okay, so let's go back to our initial system level diagram. We were able to gain some computational efficiency and scalability through the use of skills and our skill planner. But if recalling our original problem statement, we want to be able to solve these tasks from language directly. And that's something our system can't do, but that's something that these language model planning methods can. And so the next step is we ask ourselves, can we replace the task planner with a language model? And when we do that, we get language support natively. And you might ask, okay, what's different now between the way we're using the language model and the way that previous works have? Well, specifically now, the interesting element is the interface or the interaction between the language model and the skill planner, which is something that previous works don't consider. So there's all sorts of interesting planning strategies that can be explored at this intersection. And that's what we do in this next work called Text-to-Motion, which was accepted at the journal Autonomous Robots, specifically their special issue on language models and robotics. And so very similarly, we assume that our system has a library of skills, low-level behaviors, but now we also assume we have access to some large pre-trained language model such as ChatGPT. And the task is given in the form of an instruction from a human, a description of the skills that the robot has available to it, and a description of the state of the environment, a very high-level description, which is represented by the relationships between objects in the form of predicates. So the red box is on the table, the blue box is on the shelf, so on and so forth. And we assume that we can construct this textual description of the state of the environment using perception systems. And the goal this time is we want to plan both the high-level sequence of steps using the language model and the low-level continuous parameters of the plan. So, where are we placing things, where are we picking them up? And we want to come up with this plan such that it satisfies the user instruction when executed. And so the core idea behind Text-to-Motion is we're going to do this in 3 simple steps. First, we're going to ask the language model to predict goals. These are going to be goals that we test our plans against. If our plan satisfies these goals, then we know that we've satisfied the user instruction. So in the next step, we're going to try to compute a bunch of different candidate plans. And the way we're going to do this is we're going to ask the language model for the sequence of skills, psi 1 through h. This is, for example, the sequence, pick up the mug, place the mug, pick up the cup, place the cup. And then we're going to use our previous work, STAP, sequencing task-agnostic policies, to optimize for the continuous robot actions associated with this sequence of steps. And finally, we'll return the plan for execution if and only if it satisfies the goal. And we come up with a few different planning strategies in order to solve this problem. The first one is what we refer to as shooting-based planning. In a nutshell, we start with the instruction from the user. We start with the initial state of the environment and the goals that were predicted by the language model. And we pass that to the language model, represented in dark blue here. The language model gives us a bunch of different plans, so there's a bunch of different sequences. We optimize those sequences and we get predictions for what is the final state of the environment if we were to execute this plan. So this is all happening before the robot does anything. Robot's thinking beforehand. Oftentimes, none of these plans ends up being successful. And the reason is because while this method is very efficient, since we're only querying the language model once, oftentimes the language model isn't able to deduce plans for which a feasible continuous robot plan exists. But it is an efficient strategy. And so we come up with an alternative strategy where instead of asking the language model for full plans, we gradually build up the tree, the search tree, so to speak, the sequence of skills that we should be executing, where we use the language model to propose just what would be some good candidates for the next action to take, and we pick the candidate that is most likely to succeed in the environment. And then we go from there. If the state that results does not satisfy the goal, we reapply the next step of search, and we get a new set of candidates, and we do this until we reach the goal. Now, this method queries the language model numerous times during the search, and so it's very costly, but the plans are very likely to be feasible because we're building up the search tree step by step. And finally, what the full system looks like is a hybrid. We want both efficiency and reliability. So we start by doing this shooting-based planning method, and if no goals are found, we take a single step of search. We pick the best skill to execute, we predict the state that would result from that skill, and then we try shooting again. And maybe on the next step, shooting succeeds and we have the goal. And if shooting succeeds, then we don't run any more search. And so this integrates the strengths of both shooting-based and search-based planning strategies. We come up with a set of evaluation tasks similar to the ones we've seen before, except this time each task comes with a corresponding language instruction. And this time the tasks require semantic reasoning because we need to understand how the language instruction relates to the state of the scene. And we categorize these tasks in terms of a few different properties. So for example, in lifted goals, the instruction doesn't tell the LLM, the language model, what object to go for. It just says, for example, bring me any box, not bring me the blue box. So the LLM needs to think, well, which is the best box to get in this case, given the state of the environment. Our baselines are, as I mentioned before, say can and inner monologue. These are pretty seminal works in language planning. And so here's a demo of what our system looks like in the end. How would you pick and place boxes onto the rack? Instruction is given to our planner, and our planner is operating here on the left. It starts to sequence skills successfully, and it ensures that the plan will achieve the user instruction before executing anything. The baseline in the middle essentially is unable to solve this packing problem. Whereas the shooting-based strategy, which we also came up with, is successful in this case. This is probably the hardest task we consider. So we asked the language model directly, how would you get two primary colored boxes onto the rack? So it needs to think about now, which objects are primary colored and so on and so forth. And so our method, text-to-motion, is able to both capture the red and the blue item, and it also uses the hook. It automatically realizes that it needs to use the hook to solve this problem. Whereas the baseline is unable to solve this problem. And the shooting planner, as I mentioned before, suffers because sometimes the plans are not feasible in the environment. So in summary, we present text-to-motion from natural language instructions to feasible plans. It will soon be published at the Journal of Autonomous Robots, special issue in large language models. And this QR code will take you to the website. So if you want, please check it out. The result is we have now a system that is quite general. It can generalize to new tasks. It can interpret abstract goals, and it can perform in environments that it hasn't seen before. And with that, I just want to thank my collaborators and the funding agencies for funding our work. And thank you very much for your time.